So welcome everyone. My name is Aurélien. I'm one of the co-organizers of Flow, along with Peter Richtrig, Virginia Smith, Dan Alistar, Samuel Horvath, and Sebastian Stitch. So for those who might be kind of first joiners, so the goal of the Flow seminar is to provide a forum to discuss the latest results in all aspects of federated learning, which includes things like distributed optimization, learning theory, privacy, security, communication compression, and also things related to systems, hardware, and of course applications. And before I introduce today's speaker, just a quick explanation of how to ask questions during the talk. So you're welcome to ask questions throughout the talk. So, but by default, all mics are off for audience members. So you should use either the raise hand features or just write question directly in the chat. And we will monitor this, and then we can kind of unmute you so you can ask the question yourself. All right, so our speaker today is Abolfazl Hashemi. Thanks a lot for accepting our invite. So Abolfazl is an assistant professor of electrical and computer engineering at Purdue. He received previously a PhD in ECE as well from University of Texas at Austin in 2020. And did also a postdoc there at the Oden Institute for Computational Engineering and Sciences. So Abolfazl was also the 2019 Schmidt Science Fellow Award nominee from UT Austin, and also the recipient of an Iranian National Elite Foundation Fellowship. And broadly speaking, his research interests span optimization for distributed machine learning, control, and signal processing. So today he will be talking about federated learning under differential privacy constraints. And so typically the analysis of such algorithms requires some kind of Lipschitz assumption on the objective function. And of course, this is not often the case in practice. So there is this clipping strategy that is used to enforce a bound on the norm of the gradient or the model updates. But this introduces quite some problems, like some bias, also some kind of tuning issues. And so I think the topic of the talk is kind of to present a theoretical analysis of private FL with clipping, and also discuss some alternatives also to clipping. So really looking forward to the talk. Thanks a lot, Abolfazl, and the floor is yours.
Well, yeah, thank you, Aurélien, for the kind introduction. It's a great pleasure to talk about our recent work on convergence of differential deprived federated learning. This is a joint work with my collaborators at UT Austin, specifically Rudajit Jas, who's a PhD student in the CS department, as well as Professor Sujay Sangavi and Indrajit Dillon, who are professors at UT School of Electrical and Computer Engineering and Computer Science. So I want to mention that most of the credit of this work goes to Rudajit for implementing our ideas and increasing our theoretical understanding of private FL. And indeed, our primary motivation for this work is understanding the fundamental trade-offs between privacy and efficiency in federated learning and the methodologies that optimize such trade-offs. So since it's a fellow seminar, I'm sure most of us are familiar with the main steps and main setup in federated learning. But just to formalize our notation, I try to briefly describe what the federated learning problem is. So our goal in federated learning is to learn parameters of a predictive model, for instance, a deep learning classifier, in a collaborative fashion from decentralized data. In particular, we consider a distributed setting where we have n clients, client 1 through n, and each one has its own data, d1 through dn, and they're going to periodically communicate with the server to optimize a global objective f and learn an optimal parameter w star. The global objective f is the average of clients' local objective functions, fi's, where each of these fi's can be thought of as the expected loss of each client. So this is our sort of optimization problem. And there are typically two scenarios or two settings in the federated learning. The first one, this is the homogeneous setting where the data sets of each client are similar. And the more interesting and the challenging case is the setting of heterogeneous federated learning, where the datasets are different. In fact, heterogeneity, as well as this aspect of periodic communication between the clients and the server, is what sets federated learning apart from traditional distributed learning paradigm. All right, so federated learning is extremely beneficial as it requires smaller communication budgets compared to traditional settings and promotes data locality. However, since federated learning relies on information sharing between the clients and the server, like any other distributed learning setup, there is a possibility of sabotaging the security of personal data through communication. So a central question is how the server in federated learning can optimize the global objective while preserving a strong notion of privacy of client's data. So this brings us to the extremely useful and elegant framework of differential privacy, which is a popular mathematical tool that enables us to quantify privacy and the cost of privacy in training of machine learning models. At a very high level, the goal in differential privacy, or DP, is to find a way to learn basically nothing about an individual while learning useful information about the population as a whole. In other words, DP, differential privacy, argues that we may consider a learning algorithm privacy preserving if its output is not too sensitive to an individual's data. So if our algorithm is not too sensitive, then it's great. But if it's too sensitive, then DP aims to offer a way to reduce this sensitivity to individuals' data. So can we do this? Can we do this with deterministic algorithms? Are deterministic algorithms differentially private? In fact, it's a well-known result that it's impossible for deterministic algorithms to be considered DP, and there is a simple and well-known example to sort of argue why this must be the case. But in the rest of time, I'm gonna just skip this example, and if there was a question, I'll be happy to talk about that. All right, so then we cannot ensure privacy with deterministic algorithms. So what do? In differential privacy, we're going to sort of incorporate a controlled amount of random noise to the result of our analysis in order to ensure that our analysis becomes private. So if we have a low noise, it means that we're going to have weak privacy guarantees. But if we add too much noise to the result of our algorithm, then it means that we get excellent privacy guarantees, but we cannot really infer or learn anything useful from the data. So there is a level of noise that we should aim for that depends on our learning task as well as our learning algorithm. So now let's try to formalize these ideas as I just talked about and see how they can be applied to our objective, which is privacy-preserving federated learning. So first, we sort of introduced this notion of neighboring data sets. And that's really important in the definition of differential privacy. So let's consider a collection of data sets DC. Then within this data collection, we say two data sets are neighbor if they differ in exactly one sample. Okay, every data point in the data sets are the same except for this one sample. And if that's the case, then we say these two data sets are neighbor, and we denote this by this notation that says that the cardinality of d minus d prime is 1. So having this definition, we cannot precisely define what differential privacy is. So given a collection of data sets DC and a query function H that gets a data set and gives a query, a randomized mechanism M which gets a query and gives an output, is said to be epsilon delta differentially private if for any two neighboring data sets, this expression holds, this inequality holds. So what does this expression says? It says that the probability to obtain any specific analysis results on D should be roughly equal to the probability of obtaining the same analysis on D prime. So this rough equivalence is captured by these parameters, epsilon and delta. So these are our privacy parameters. The smaller these two are, the higher our privacy guarantees is, and these two properties are going to be closer to each other. So there is also this terminology in the literature that if delta is equal to 0, then we sort of refer to this definition as pure differential privacy, and otherwise we refer to it as approximate differential privacy. All right, so we say that let's say that we have a query function h, right? And how can we design a differentially private mechanism? There are many ways to do this, but a simple way is to add, essentially set our mechanism M to be an additive random Gaussian noise. And this approach is known as the Gaussian mechanism in the literature. All right, so let's say that we want to use this Gaussian mechanism, but how much noise power or noise variance is adequate in order to ensure that we achieve differential privacy guarantees. There's this nice theorem that sort of formalizes our intuition that the noise power should increase if we want tighter privacy guarantees, and it should also increase if our algorithm is too sensitive. In particular, let's set delta to be the maximum sensitivity of our query function over all neighboring datasets. Then, if we set our mechanism to be the Gaussian mechanism, essentially a random additive Gaussian noise, which is 0 mil, and its power satisfies this equation or this expression, then this mechanism is going to be epsilon delta differentially private. As we see, the noise power here increases with sensitivity, increases quadratically with sensitivity parameter delta, and also increases if you want tighter privacy guarantees. So for tighter privacy guarantees, we require a smaller epsilon and delta, and doing so means that we need to incorporate more noise in our mechanism to achieve this tight privacy guarantee. And this essentially matches our expectation. All right, so let's see. So one last point about differential privacy is that, so we talked about Gaussian mechanism, but actually similar results exist for other mechanisms, for instance, the Laplace mechanism and the discretized or truncated version of Gaussian or Laplace mechanism, which might be useful in scenarios where, for instance, we only communicate low precision messages. All right. Okay, so now that we are familiar with differential privacy, now let's go back to our main problem and see how we can apply DP in federated learning. To this end, let's first discuss the main federated learning algorithm, which is federated averaging. Right. So as we discussed before, we have a number of clients. Let's say we have a number of connected cars that intermittently or periodically communicate with the server after locally optimizing their objective functions for a few local steps. So after these clients communicate to the server, their parameters, then the server aggregates them and it's going to send this result back to the clients to start the next round of training. More specifically, for the local updates, clients typically do E steps of local optimization, say, for instance, by using gradient descent. Specifically, we're going to have a first order update like this, where we use a step size of eta. Then, after the local update is done, the clients send their current parameter and their updates essentially an update, which is going to have this form to the server. So the update U of client I at communication step K is just the difference between the current global parameter and the current local parameter normalized by the step size. And yeah, this essentially captures some notion of generalized gradient, if you imagine, if you use first order updates in our local clients. So here a common strategy is that in every communication rounds, our clients are sampled at random for participation. However, because this work is about differential privacy, for a technical reason that is essential to guarantee differential privacy guarantees, we sort of consider a setting where each client communicates with probability R over N. So instead of having exactly our clients participating in every communication round, the expected number of clients that participate in every round is R, but it might be higher or lower than R. All right, so after these updates are received by the server, then the server performs a global update that again has a first order form, but potentially with a different step size, let's say beta. But in this fork, we sort of set beta and eta to be equal, and we're going to use constant step size. All right, so what I just described is just essentially one communication round, and we're going to repeat this process for a total of K communication rounds. So the total number of communication rounds is going to be capital K. All right, so once the training is done, it's time to output a set of parameters. And one way to do this is to randomly sample a parameter from all of the K global models that were learned at the end of each communication round. Okay, so in practice, we typically take the last update, but it's a common practice in analysis of optimization algorithms to sort of sample parameters at random according to some distribution, which is typically the uniform distribution.
So Abolfazl, maybe just a quick question here to make sure, right? This is indeed just for kind of technical issue related to the optimization guarantees, not related to privacy, that you are taking a random iterate at the end, or will you exploit this?
So this is related. Yeah, this is related to just the way that we analyze the algorithm and derive convergence guarantees. But this is step where we sample clients, and essentially every client gets to communicate to the server with some probability. So that's because of the privacy guarantees.
Sure. Okay. Just wanted to check that you are not going to leverage this in the privacy analysis later.
Yes.
Okay.
Yeah, thank you. That's a good question. All right. So this essentially what I just described is a version of federated averaging, some variations. But now let's see how we can sort of make this private and where we should tackle this algorithm to ensure that the privacy of the clients is preserved. So, and in order to do that, we need to look at the update that the client sent to the server. This update, as I mentioned, it contains information about the local gradient of the clients, which is considered sensitive information. Okay, so it needs to be private, and to do so, we're going to incorporate differential privacy. All right, so differential privacy guarantees, again, are achieved by incorporating random noise, and the noise of this random noise is gonna depend on the sensitivity of our query algorithm. In the case of federated averaging, what's gonna matter is that this sensitivity parameter delta, which again shows up in the variance of the noise, grows with the norm of the update UI. Okay, so the higher the norm of the update is, then the higher the sensitivity, and therefore we need to incorporate more noise to achieve a target privacy guarantee. So say for the timing that we have a Lipschitz function that we are optimizing. for instance, let's say our function is G Lipschitz, and that's essentially to say that each gradient is uniformly bounded by this parameter G. Okay, so if you have Lipschitzness, then this norm, the norm of the update, is at most G times E. Why? Because we take E steps of local gradient descent. So we're going to accumulate E gradients. Each of them is bounded by G. Therefore, the total norm of the update is going to be at most G times E. Okay, so if that's the case, then this norm is uniformly bounded, and therefore the sensitivity is going to be uniformly bounded, and we can incorporate a controlled additive noise in our updates to ensure privacy guarantees. In general, we need to limit how large the update can get. Okay, and that's because we don't. That might be because we don't know this constant G, the bound on the norm of the gradients, or even our function is not Lipschitz, so G doesn't exist at all. All right. So if we don't limit how large the update you can get, then it is impossible to remove the unbounded impact of one client on the output. Okay, so if you don't limit this one client, our update is going to be too sensitive, such that we cannot even guarantee differential privacy. So what do we do? What do we do to sort of limit this update? We're going to simply clip it. Okay, we're going to clip the update first, and then add a controlled noise to it. And this will ensure that we have bounded sensitivity, and we can incorporate a controlled noise in our update. In particular, we're going to use this operation. Okay, so this is our clipping operation. We just take our update U, but we're going to consider two cases. Let's say that we have a clipping threshold C. If the norm of our update is less than C, we don't do anything. We just send the update as is, plus the noise, the additive noise that we're going to incorporate for privacy. However, if the update norm is too large, in fact, larger than C, then we're going to clip it to ensure that the norm is smaller than C. And then we're going to incorporate some noise with some variance that I'm going to discuss next, and then send this to the server for aggregation. All right, so by employing this approach, we can simply generalize the result of Abadi et al. From 2016 that sort of analyzed a differentially private version of SGD to establish a differentially private Fed average with clipping is going to be epsilon delta private. And the only condition that we need is that the variance of the noise must be given by this expression. So here the variance depends on the number of parameters. Q here is an absolute constant, which is positive. Capital K, remember, is the number of communication rounds, and this appears here because we're going to ensure that every round is differentially private. We're going to see C square here, again, because the variance of the noise depends on maximum sensitivity. And in this case, it's going to depend on the clipping threshold. We also see dependence on the number of clients as well as the privacy parameters epsilon delta. All right, one thing to note here is that this theorem does not discuss the convergence of differentially private Federated averaging with clipping. It just says that if we incorporate this amount of noise, then our algorithm is going to be differentially private. All right. And now that we've covered the necessary background, I'm going to move on to our first contribution in this work, which is on the convergence of differentially private Federated averaging with clipping. All right, so I'm going to quickly discuss the main assumptions that we need in order to derive our theoretical results. And yeah, so these are typically the standard assumptions or definitions. The first one is that we assume that our function, the global function as well as the local functions are convex. We assume that the functions are L smooth, and that's to say that the gradients are L Lipschitz. And if our function is twice differentiable, then smoothness means that we can get a nice quadratic upper bound for our function at any given point. And finally, we're going to quantify the amount of heterogeneity. Okay, we're going to analyze federated learning algorithms in general heterogeneous settings. So we need to sort of quantify how heterogeneity is going to affect the convergence rate. So to do so, a simple way is by measuring how different the local function evaluated at the global optimizer are when compared to their evaluations at local optimizers. In particular, let's say that W star is the optimizer, is the global optimizer. Let's define delta I star to be the difference between Fi at W star and Fi evaluated as local optimizer. Then the heterogeneity of the system is quantified by some increasing function, or rather non-decreasing function of these delta i's. Specifically, what's going to happen is that a function of these delta i's is going to appear in the convergence error of federated learning algorithms. All right. So now we are in a position to sort of state our theorem on the convergence guarantees of differentially private federated averaging with clipping without assuming Lipschitzness. In particular, suppose that each of these functions are Fi, each of these Fi functions are convex and L smooth over Rd. Then define this parameter rho, and I'm going to discuss what rho is in a moment. It's essentially a cost of privacy. Then there exists constant local and global learning rates eta and beta, and a lower bound on the clipping threshold C low, such that for any clipping threshold C that is larger than C low, if we use this many communication rounds, then we're going to get this convergence result. So let's sort of see what this says. Let's dissect this. So here on the left-hand side, we have a convergence criterion that may seem non-standard at first, but it has two familiar-looking parts. Okay, the first part here is a function suboptimality, and the second part is proportional to the gradient norm. So we have seen this in typical analysis of optimization algorithms. Function suboptimality, for instance, is a typical convergence metric when we are analyzing convex and L-smooth functions, and when we are analyzing non-convex functions that are smooth, then gradient norm is again another familiar convergence criterion. All right, so this criterion appears in the theorem as we don't require the Lipschitzness of local functions. And I'm going to actually talk about a simpler, more familiar looking result in the next slide if we assume Lipschitzness. And I should also mention that given our current analysis techniques, it seems that it's unavoidable to sort of get something nicer as our convergence criterion. All right, so whatever this is some convergence criterion. So let's put this out of the way, and let's sort of focus on the more important part, which is the convergence error. Here, the convergence error has essentially two parts. The error stems from two sources, the purple source and the orange source. The purple source, or the purple term, that stems from the initialization, while this orange term is due to heterogeneity. Right? So here in the convergence error, we also see this parameter rho, which is defined here. And as I mentioned briefly before, rho is essentially the cost of privacy. Okay, so rho increases if we want tighter privacy guarantees. All right, so if I decrease epsilon and delta, then it means that I require a higher level of privacy, and that's going to mean that this parameter rho is going to increase. So it's meaningful to say that rho captures the privacy cost. All right, so from the convergence error, one thing that we can observe is that in contrast to non-private setting, the convergence error in private FL is non-vanishing. Okay, so this term doesn't vanish; it's going to stay there. Our analysis actually shows that the second term, the effect of heterogeneity here, can be in fact reduced arbitrarily if we are willing to increase the number of communication rounds K. But the first term, the effect of initialization, is going to remain there, and we cannot do anything about it. All right, so as I promised, it's possible to obtain friendlier results under Lipschitzness. In particular, if we assume G Lipschitzness, then we can set the clipping threshold to be G times E, and that ensures that our updates are uniformly bounded by G times E. And this means that no clipping occurs if we use this clipping threshold. And we can get rid of this gradient norm term in the convergence result to obtain this simpler convergence rate for differentially private Federated averaging with clipping. Again, we see the convergence error depends on two terms, the initialization term and the heterogeneity term. While the heterogeneity term can be controlled by increasing K, the effect of initialization is not going to vanish. And in fact, if we set the number of local updates E to be constant, order of constant, then this bound is going to match the existing lower bounds for centralized convex and Lipschitz case with respect to the dependence on rho, the cost of privacy. So looking at this result, one may ask, okay, it seems that this the number of local steps E adversely affects the convergence. Is that really the case? Are multiple local steps beneficial or detrimental to the convergence of private federated learning algorithms? And this brings us to the next contribution of this work.
Maybe, if you don't mind, like I would like to ask a question, maybe on the
sure, absolutely.
previous result, I guess even previous slide. So, why do you need to assume this row can be much bigger than one, in fact, right?
Oh yeah, it can be much bigger than one, but this is essentially the interesting case that it would make sense to sort of analyze to derive privacy guarantees. The other case is it's not going to make sense.
In the sense that just the error is going to be huge and potentially bigger than at initialization or something like that.
Yeah, exactly. The other case means that, I mean, we are recording too tight privacy guarantees. Therefore, we need to incorporate more noise, a lot of noise, and it's impossible to get good convergence.
Okay. And I guess in the result here, it should be C low instead of C, right? I guess C low lower bounds all the C's. Yes.
Yeah. So you'd want to use the smallest C that you can do, you can use, right? Yeah. But this essentially holds for any C. So essentially, I just want to point out that we cannot use any C. C there is a lower bound on C, on how small C can get, right? And this lower bound depends on parameters such as heterogeneity and things like that. Yeah.
I see. Okay. It hides a condition on C. Okay.
Exactly. So the whole purpose here is to hide the condition on C, but there exists a condition on C, on how small C can get. All right. Yeah. Thank you. Very good questions. All right. Yeah. So I think I was here. Yeah. So we were discussing the effect of multiple local steps in the convergence of differentially private federated learning algorithms. At the high level, increasing E mitigates the effect of initialization at the cost of increasing the effect of heterogeneity in the convergence error. So sort of the best value of E that we can use depends on which of these sorts of errors is more dominant. And of course, it also depends on the cost of privacy role. Unfortunately, a precise quantification of this intuition that I just talked about is not possible using the assumptions that we discussed so far. Therefore, what we're going to do is that we're going to resort to basically a new assumption on curvature of our functions. And I should point out that similar versions of these assumptions sometimes appear when we want to drive convergence bonds to second-order stationary points of first-order algorithms. Okay, so let's see what this assumption is. This assumption is stated here, but basically it says that the difference of the gradients at two consecutive updates should not be or cannot be arbitrarily small. And this how small they can get is captured by this parameter lambda. So I mentioned that there is a connection to curvature, and let's see the connection. And to get this connection, observe that if we require a very small step size eta, then one thing we can do, we can sort of approximate this term if the second derivative exists with this term. So this term is going to have is going to be proportional to eta, and also the norm of the Hessian times the gradient, the product of the Hessian and the gradient. So, so basically what we are assuming under this assumption is that this inequality holds, all right? And this looks very similar to definition of an equivalent definition of a strong convexity for functions that have that are twice differentiable. But it's going to be actually weaker. Why? Because in a strong convexity, we're going to assume that an inequality like this holds for any vector. So we're going to replace this gradient with any vector. But this assumption says that this inequality needs to hold only for the gradient. All right. So we're going to require this new assumption, and we're going to utilize it to sort of obtain the following convergence result that says that there exists a choice of C, the clipping threshold, that's going to depend on E, such that we get this convergence guarantee. Okay. We're going to assume Lipschitzness here. So let's analyze the convergence guarantee. There are two terms again. The first term is identical to what we saw in the previous results. It's going to depend on G and the initialization. But what's going to change is the second term. So this ORI term essentially is going to be different, and in fact, it's going to be smaller than what we saw before. Why? Because we're going to have this new negative term here. So what does the result mean? It means that if it happens that this inequality holds, essentially the degree of heterogeneity is less than the product of the initialization error and the cost of privacy and a problem-dependent constant, then having a large value of E is going to be beneficial. In fact, it's best to set E to its maximum possible value, which given our theory is 1 divided by 2 times rho. However, if this inequality doesn't hold, then it's beneficial to use a smaller value of E. In fact, it's best to set E to be 1. All right. So doing so, so let's say that this inequality holds, right? And then we can increase E. So what's going to happen is that this negative term is going to sort of reduce the impact of initialization in the convergence error. So that's why increasing E under this assumption means that we're going to sort of get better convergence errors. All right, so let's summarize what we have discussed so far. We talked about the convergence of differentially private federated averaging with clipping, with and without Lipschitzness, and we also discussed the role of the number of local steps E in differentially private federated averaging with clipping. Okay, so our focus has been so far on using clipping to reduce sensitivity and provide privacy guarantees. But in terms of convergence results, clipping actually has a potential issue. And that's the following. So this is the operation of clipping. So what's going to happen is that as our algorithm converges, then the norm of this update is going to decrease. Why? Because the local updates are going to get closer to the global updates, typically. Okay, so what it means is that, going back to the definition of clipping, if the update norm becomes small, then it's going to be the case that clipping never occurs anymore. Okay, so clipping never occurs anymore, but this doesn't mean that the additive noise that we need to incorporate for differential privacy guarantees also decrease. Why? Because the variance of the noise, remember, is going to be proportional to C, the clipping threshold, not the norm of U. So one may ask, okay, can't we just adaptively reduce C, for instance, by incorporating information about the norm of U as the algorithm converges? So that would be, that's actually a great observation if someone suggests this. However, it turns out that doing so will reveal sensitive information about the client, and it won't be possible to show differential privacy guarantees. So essentially, for a clipping parameter, we only need to use global information, and we are not allowed to use local information. So then with clipping, what's going to eventually happen is that the update norms are going to get smaller and smaller while the noise remains at large. And that means that we're going to enter a low SNR regime, where the added noise is going to become dominant and is going to hurt convergence. All right, so it's been a while since we've seen a figure, so let me show you part of our results that sort of illustrates this phenomenon of entering a low SNR regime. So I'm going to discuss the details later on, but what we're doing here, we are sort of running differential federated learning on synthetic convex quadratic functions, and we are varying our parameters, C and the learning rates. So in the figure, this star is the initialization. The blue dot is the optimum that we are trying to converge, and this green curve corresponds to the trajectory of the clipping approach projected on 2 dimensions. So as these figures show, the trajectory becomes noisier as the algorithm converges. So initially, there is less noise, but as we get closer and closer to the optimum, then we see more noise, okay? And that sort of supports this idea that we're going to enter a low SNR regime where the norm of the update is small, but the amount of noise is high. Therefore, our convergence is going to get hurt. Okay, so essentially, the observation is that clipping is going to hurt SNR. But is it possible to look for an alternative that ensures clients' updates have higher SNR values as we converge to a solution? So that sort of brings us to our last contribution of this work, which introduces normalized update in differential privacy. Effectively, what we propose to do is to use normalization instead of clipping and run differentially federated averaging with normalized updates. So this is our operation. It looks very much like clipping, except that we don't have this minimum at all. And we're going to sort of ensure no matter what our update is, it's after applying normalization, its norm is at most C. So this essentially ensures, as I mentioned, that the update is going to be uniformly bounded, and at the same time, noise is not going to overpower the update anymore. Why? Because even if we are closer to the optimal and our update norm is small, after normalization, it's going to get compensated and it's going to become larger and more significant compared to the additive noise. So another observation that sort of relates normalization to clipping is that if we use very small clipping thresholds, then normalization and clipping become equivalent. Because in this case, the second term in the minimization here, going to essentially be active, and a clipping operation will always be minimum so clipping is going to be essentially active if we use a very small parameter C, and that part is essentially what we see in normalization. All right, so what we have done in the paper, we have analyzed the convergence of differential private federated learning with normalized updates, and we provide a theoretical comparison of clipping and normalization to see which one is more advantageous. Unfortunately, the results are rather involved because to do a precise comparison, we need to rely on the unabridged version of our convergence theorems that I couldn't discuss in this talk. So I'd like to refer you to section 5.1 and remark 1 in our paper for a precise comparison. But the main takeaways are as follows. First, our theory shows normalization enjoys a smaller effect of initialization on convergence. So in that sense, normalization is more advantageous to clipping. Secondly, when it comes to the effect of heterogeneity, it's not easy to characterize whether normalization or clipping is better. But that's going to be fine. Why? Because as we talked about before, we can control the amount of heterogeneity and its impact on convergence by increasing the number of communication rounds. So overall, because normalization has a better dependence on initialization, it's going to have a better asymptotic convergence as well. Therefore, our theoretical results seem to recommend that we should do normalization, especially if we can afford to have training with larger values of K. All right, so that's essentially the end of our results. And now I'm just gonna discuss some of the experimental results that we have in the paper. So the goal of the first part is to try and verify our theoretical results in a controlled environment. And to do so, we consider, as mentioned before, synthetic convex quadratic problems with randomly generated data. And in particular, we set epsilon delta to be 5 and 10 to the minus 6. We set the number of communication rounds to be 500, the number of local steps E to be 20, and we set the number of clients to be 100, and we assume full device participation. So this means that every communication round, all of the devices are going to participate. So we're going to also try different random initializations as well to capture the effect of initialization. And we're going to vary our main parameters, the step size and the clipping threshold, to see how they affect the convergence. So first, let's revisit the 2D trajectory curve that we saw earlier for clipping, but now let's sort of see how normalization is doing compared to clipping. So here we should focus on this red curve because that corresponds to normalization. And as we can see, compared to clipping, normalization reaches closer to the optimal than the clipping approach, and that's sort of consistent with our theoretical results that says that normalization enjoys a better convergence guarantees compared to clipping. All right, so the next sort of set of results relates to the convergence curves for various learning rates and two different clipping thresholds, in particular C equal to 40, which I consider a small clipping, and C equal to 100, which I consider a large clipping. In the figure on the left, we sort of see that normalization and clipping are almost identical, and that's to be expected because when our clipping threshold is small, then we are going to always clip, which means that the operation of clipping is going to reduce to the operation of normalization with the same parameter C. Okay, so we expect for a small clipping thresholds, normalization and clipping to do almost the same. Now let's consider the larger clipping threshold of C equal to 100. And as we can see here in the figure, there is a huge gap between the performance of clipping and normalization. And that's to be again expected because by using large clipping, clipping and normalization are quite different. And as we discussed before, clipping is going to get hurt by a high degree of added noise that is required for privacy guarantees. All right, so finally, we sort of show the signal to noise ratio or SNR of the updates for both normalization and clipping to see whether this is consistent with our theoretical result that says normalization enjoys better SNR compared to clipping. Again, we consider two regimes of a low clipping and a high clipping. In the low clipping regime, the SNR of the two approaches is roughly the same. And again, it's expected because in the low clipping regime, normalization and clipping are roughly equivalent. But as we increase the clipping threshold, these two are going to become quite different. And as we can see, normalization is going to enjoy a much higher SNR values compared to clipping. All right, and finally, we have also conducted experiments on standard logistic regression tasks on datasets such as Hashemi, C410, and C400. And here I'm showing the average test accuracy over the last 5 rounds. And as we can see, given a target differential privacy guarantee, a set of parameter epsilon delta, normalization enjoys better convergence compared to clipping and closes the gap between private and non-private federated learning. To summarize the talk, our goal in this work was to provide a convergence analysis of private federated learning. And we started by establishing convergence of differentially private federated averaging with clipping without requiring the assumption of Lipschitzness. And we focused on smooth convex loss functions. Our results show that the effect of heterogeneity can be controlled by increasing the number of communication rounds. However, the effect of initialization is going to remain in the convergence bound, and that's in contrast with what we see in non-private optimization. We also argue that if the degree of heterogeneity is less than the product of the distance between, so essentially I'm talking about this condition. If the degree of heterogeneity is less than our initialization error times the cost of privacy times the problem-dependent constant, then it's going to be beneficial to increase the number of local steps because that's going to reduce the impact of initialization in the convergence error. In the other part of the talk, we sort of make this theory-guided recommendation to use normalized client updates instead of clipping for differentially private federated averaging, because doing so has 2 advantages. It's going to increase the SNR of the clients, and it's going to have theoretical benefits when it comes to convergence over clipping because of the mitigation that we see in the effect of initialization. And with that, I'd like to conclude the talk, and thanks everyone for listening. So here's the title of our talk. Here's a link to the paper on archive. And here's a small advertisement for my group. We are hiring postdoc and PhD students in the broad area of optimization for machine learning. And with that, yeah, I'd like to thank you, everyone, and I'd be happy to hear your questions and comments.
Thanks a lot, Abolfazl, for the nice talk. So we have a bit of time for questions. Do you have any questions in the audience, either by the chat or you can raise your hand? Maybe I can ask one first. So it's a very basic question. You went a little bit fast at the beginning, I guess, on the trust model. So my impression by looking at the cost of privacy is that you consider probably a trusted server and publishing the final model at the end, something like this. This is the setting, right?
Yeah, exactly. Yeah, we are considering a trusted server. So so in our implementation and in fact in our algorithm, we can incorporate noise locally because we are using this additive mechanism, right? But essentially you're right? So what we need is to add the noise or a general mechanism at the server. So we need to require a trusted server. Yes.
Yeah. Otherwise, you wouldn't have the 1/n factor in row, right?
Exactly.
And maybe connected to this, so in federated learning, people look at maybe two kind of neighborhood notion, right? For DP, there is kind of let's say data point level and client level in terms of whether you want to hide, the impact of one data point or the entire data set of one client. So here, I think when you presented DP, you talked mostly about the individual data point level, but at the same time here, it's a bit abstracted away, I guess, the impact. I was a bit wondering whether the analysis can be easily adapted back and forth to these two levels. When you do individual data level, typically you want to rely on maybe a subsampling argument, unless you take full batch. Okay, so can you maybe clarify a bit?
Yeah, sure. Yeah. So let's go back to this setting again. So if I understand,
because I think you also assume full batch gradient, right?
Exactly, right. So that's a good point, right? So we are going to incorporate full gradient information locally. So we're not going to do a stochastic gradient. We're going to do gradient descent, which means full batch, right? And after updating locally, we're going to send this vector to the server. So we would send this vector to the server if we didn't, if we weren't considering the private setting. But for privacy, we're going to add noise to each of these, right? But we're going to trust the server. So adding noise locally, because the noise is additive, it's equivalent to adding the noise at the server.
Yeah. So I mean, so depending on whether you consider data point level or client level would maybe reflect itself. If you, at least in the Lipschitz case, it would just change the Lipschitz constant, would be divided by n or by m, let's say the size of the local data set somehow or not, depending on the level that you're considering. Okay.
I think that's one way to sort of argue about that, right? So effectively, I guess if we don't use full gradients, then what's going to happen at a high level is that by using a stochastic gradient, the sensitivity is going to go higher, and we're going to require a larger noise. Is that what you're saying?
Not really. I guess I was pointing out. So even if you assume still full batch, but now I don't know. I think your results, to me, they are more clear by assuming this client level DP, where you want to hide the impact of an entire data set of one client, because you clip the individual updates and not the individual gradients. If you do multiple steps, and okay, so I think you could adapt to individual data point level, at least if you, in the Lipschitz case. Maybe in your generalized case, it's the dependency on the number of data points of the clients become a bit abstract, because okay, so this one point, and then
I see your point. Yeah, so that's actually a good point. And so we are working in sort of extending our theory to other scenarios as well, as you mentioned, right? So other type of privacy guarantees or privacy models, and other form of local optimization methods. Yeah.
Right. Okay. Thanks a lot.
Yeah, sure. Thank you. That was a good point. Appreciate it.
No, this is someone clapping. So I guess for the talk. Do we have some more questions? Okay, so far not. So maybe I can ask another one then.
Yeah, sure.
I was wondering a bit whether your analysis allows to maybe to quantify a bit the effect of the learning rate, because it's been observed right already in previous work that the clipping, the choice of clipping threshold and the choice of learning rate are kind of tied together, and sometimes, at least empirically, you can kind of fix one and tune the other somehow. And so I think this is also related to this signal to noise ratio. I mean, one way to maybe avoid that the noise has a large impact towards the end would be maybe to also use a little bit smaller learning rates. So I was wondering whether your analysis
exactly. So that's also a good point,
about
right?
that.
So that's a really good point. Yeah, and in fact, one of the reasons that we sort of require we impose this condition on rho is that rho appears in parameters. It appears in the step size. It appears in E. It appears in C. And so I guess what we did is to sort of try to identify what are good parameters, what are good values to choose for these parameters in order to get a convergence result, right? And to get that, everything is going to depend on rho. So we can get a more involved, if you will, result that requires that applies to broader range of parameters, and we have that mentioned in the paper. But for the purpose of the talk, I sort of focused on a nicer and simplified version of our full theory, and this version, in fact, requires the dependencies that you pointed out.
I see. And empirically, did you check whether, let's say, tuning the learning rate or maybe using a decreasing learning rate with clipping maybe can achieve something similar to the normalization or not? I mean,
so we tried various learning rates and clipping thresholds. So I would say, so maybe C equal to 100 is a very large clipping parameter. But so what we sort of saw is that so for various learning rate, if we sort of consider a specific clipping threshold for various learning rates, we sort of observe the benefit of clipping. The benefit of normalization over clipping if you have a large clipping threshold. But obviously, if the clipping threshold decreases, then the two algorithms are going to behave similarly.
I see. And maybe for large C, you would be able to compensate with clipping by choosing very small learning rate, but then this would require doing many more.
Exactly, rounds. So that's possible. But I mean, if you use a very small learning rate, then what will happen is that it's going to take too long for the algorithm for the clipping to converge. Yeah.
Okay, sounds clear to me. Great. It doesn't look like we have any more questions. Oh no, we do have questions now. Okay, so let me mute Paul. Okay, I think Paul, you can ask your question. We can only hear you very low.
Okay, is it better now?
A bit, but still very low, at least for me.
I just okay. It's
that works.
Is it?
Yeah, it is fine now. We can hear you.
It's fine. Okay, sorry. So thank you for the presentation. It's very interesting. So I have maybe a bit of a naive question. I'm not sure I understood correctly. So I have the intuition that this normalization, in fact, what you do is you end up amplifying the signal when it is very low, so that the noise you end up adding is less important in comparison with the signal. Is it a correct intuition?
Exactly. So that's a correct intuition. And as you pointed out, what will happen is that when the update nodes are small, then by normalization, what we're gonna use actually in the algorithm is gonna be more significant to the noise.
Like you amplify it to fix the norm? Do you think there would be other possibilities of amplifying something between the actual value and fixing the norm to 1? Could it maybe lead to some improvement, maybe because you would decrease the noise that's due to the fact that you rescale the actual value in comparison?
Yeah. So if I understood your question correctly, that you're asking about setting this C to be 1 in normalization such that the norm of the update is always 1.
Maybe something a bit in between fixing the norm of this U to C and just keeping it to U. I don't know, maybe like using the squared or the square root of U or something that would end up being between this hard threshold of C and just meeting this threshold and just between like maybe other single amplification scheme. Could this be of some interest, or is it?
Yeah, so I think that's a good question. So perhaps relevant to this, so I'm actually actively thinking of better ways to improve SNR while preserving privacy. In particular, I'm looking to see whether we can sort of have a sort of a parameter-free operation, if you will, right? That can sort of do this automatically without incorporating any C or anything like that. But currently, at least the current algorithm that we have and the current analysis we have, it's unfortunately limited to this specific way of enforcing normalization.
With having to use private values to set this value, and then it's okay. Thank you for your answer.
Yeah, thank you.
Thanks. So yeah, maybe in some applications, if you have some prior on how the gradient should look like, I guess maybe you could denoise somehow.
Okay, leveraging domain knowledge. Yeah, that's exactly a practical way of doing that. Exactly.
Right. Okay, let me unmute Nidam, who also has a question. Go ahead, Nidam. I don't think we can hear you. Looks like you are unmuted, but there is no sound. Feel free to type your question in the chat. Otherwise. Okay, doesn't look like we can hear you at all. Maybe you are typing the question, I don't know. Let's wait for just a few seconds, but if not, we will release you. Okay, Nidam is typing the question.
Yeah, sure.
If you don't mind, if you still have a couple minutes to stick around.
No, absolutely. I mean,
that's great.
Thank you. Thanks, Nidam. Yeah. Yes. Yeah. Yeah. So yeah. Okay. Yeah, exactly. So there is a good connection to political step size and some area results on using normalization in optimization. So actually, I think even Nesterov has a paper in 1984 on the analysis of normalized gradient descent for quasi-convex functions, and there was a paper a few years back on analysis of stochastic normalized gradient descent by Ilat Hazan and his collaborators. For quasi-convex functions, which are a specific class of non-convex functions. So there is a good connection, as you point out. So even if you have okay. So even if you have additional bond on heterogeneity, you have an approximation of the numerator. Yeah. So unfortunately, I don't know. It's no, it's a good question. Yeah, actually, yeah. So unfortunately, I don't know the answer to this. But as Ardian pointed out, there are ways to sort of facilitate the tuning of the parameters that we require in private learning. But what I'm looking for is something that is completely parameter free, without sabotaging the integrity of privacy. But yeah, but I'm going to follow up on your comment and see whether we can sort of leverage some ideas from polygon step size to sort of get rid of this tuning C. Yeah, anytime, yeah, please feel free to send me an email.
Great. Yeah, I think this can be followed up by email between you guys, I guess. Yeah. Thanks a lot for the nice talk and staying a bit of extra time for questions.
No, thank you. Thank you for inviting me. It was a pleasure giving the talk and hearing your comments and questions. Again, I'll be happy to answer any questions you might have over email.
Sure. Sounds good. Thanks a lot again for the talk, and bye-bye, everyone.
Right, yeah, thank you. Bye.
Bye-bye.